Hi all, welcome to part 2 of Nucleon scattering. In the previous lecture, the topic of discussion was low energy nucleon scattering. When I say low energy nucleon scattering, it just means the energy of the incoming projectile beam is much less than 1 MeV. Now, if we proceed to scattering, which is performed with higher projectile energies, then we are talking about high energy scattering. Then we get certain interesting information about nuclear forces which were not seen in low energy scattering. A graph has been plotted with phase shift on the y-axis and the energy of the projectile beam on the x-axis. There are three different curves which have been plotted and they have been named triplet S wave, singlet S wave and P wave. Now what does that mean? Obviously from the notation of that we have seen in atomic spectroscopy and all, we know S corresponds to L equal to 0, P corresponds to L equal to 1. Okay. Now what do these mean actually? If you remember the scattering experiment explained in the previous lecture, we had a beam of neutrons coming in, falling on a target which contains protons, and these neutron beam gets scattered. Okay, the incoming projectile beam can be considered as a superposition of various angular momentum states. Okay, which means there are L equal to 0 neutrons, there are L equal to 1 neutrons, L equal to 2, etc. But which of these participate in the scattering process actually depends on the projectile beam energy. If the energy of the projectile beam is less than 1 MeV, only the L equal to 0 neutrons participate in the scattering process. L equal to 1 starts contributing only when the projectile beam energy is increased beyond, say, approximately 20 MeV. So you can expect higher L values to contribute only when you go for higher energies for the projectile beam. Now here we are talking about high energy scattering experiments. So you can expect the energy of the projectile beam to be higher. So as expected, you can see in the x-axis the energy of the projectile beam is given in mega electron volt. In our previous lecture, we had seen a graph with energy of the projectile beam given in electron volts. That was for low energy scattering. But here we are talking of high energy scattering and you can see the difference in projectile beam energies. Now, of the scattered neutrons, there will be L equal to 0 neutrons, there will be L equal to 1 neutrons, etc. And that is what we have plotted here. For L equal to 0 neutrons, we have two curves, and for L equal to 1 neutrons, we have a curve. And on the y-axis, we are plotting the phase shift. Okay, the calculated or the uh, detected neutrons, and we are plotting the phase shift for each of the neutrons detected. Now, here for the S neutrons, you can see there are triplet S wave and singlet S waves. Now, what does that mean? Triplet S wave corresponds to the scattering event where the incoming neutron and the proton spins in the protons present in the target. Both their spins couple to give a resultant of 1. Such scattering events have been depicted by triplet S wave, and singlet S wave corresponds to scattering events where the spins of neutron and the proton couple to give a resultant of 0. Okay. And the general observations from the graph, you can see the low energy scattering regime, say 1 MeV and all, that is close to this origin. See, close to this origin, if you look at the contribution from L equal to 1 is 0, isn't it? There are only non-zero contributions from L equal to 0. So this is consistent with our previous lecture observations that for low energy scattering there is no contribution from L equal to 1. For low energy scattering only L equal to 0 contributes, and L equal to 1 starts contributing when the energy of the projectile beam is increased. Okay, so you have a non-zero phase shift coming in for L equal to 1 only when energy of the projectile beam is increased. Now in the case of the S waves, you can see that phase shift is positive up to a particular energy. Here it is approximately say 300 MeV, and beyond 300 MeV projectile beam energies, you see that the phase shift reverses sign. It changes sign from positive to negative. Now, how do we explain for this change in sign of delta, and what is the inference that we can make out of such a sign change? Okay. For the scattering experiment, if you remember, we had considered a potential well with the depth minus V0, and we had considered that our free particle is coming like this and it is passing through the potential well and it's going after the scattering process. And we had solved the Schrodinger equations and we had obtained solutions in the first and second regions like this, where solution in the first region is A sine capital KR, where capital K is this thing. It is root of 2m into V0 plus C by H cross. And in region 2, the solution is C sine KR plus delta, where delta is the phase shift introduced upon scattering. And the periodicity is given by Kr, where K is root of 2me by H cross. Visibly itself you can understand capital K is greater than small k. Okay, so we are going to check what really happens to the wave function upon scattering. So for that, as a reference, I am plotting sine small kr curve. Okay, it is something like this green curve. It goes to a 0 at a particular value of R2. At a particular value of R2, this argument becomes equal to pi. And which value of R, for which value of R does this curve go through 0? It is R2. Okay, let it be like that. Now we are going to see what happens to the wave function. Okay, in the first region, our solution is sine capital KR. Okay, since our capital K is greater than small k, this function will reach different positions earlier than the green line, isn't it? See, for the same, you have R on this x-axis, isn't it? So for the same value of R, KR will, KR is greater than small kr, isn't it? Since kr is greater than small kr. For the same values of r, since k is greater, kr will reach the required positions earlier than small kr. So the function is, see, it becomes a maximum earlier, then it starts declining, then only the other one becomes a maximum, then it starts coming down faster than the second one. Okay. Now, then it goes to region 2. But when it reaches region 2, there is no potential in region 2. Region 2 V0 is 0. So capital K and small k are the same, essentially the same. Now in the second region, it is having the same periodicity as this one. Okay, here also it is Kr. Here also it is Kr. But the argument is Kr plus delta, isn't it? So there will be a difference between these two sign functions, which is delta. Is it clear? It will behave like this red line will behave exactly like the green line, but except for the fact that they won't coincide because there is a phase shift introduced upon scattering. Okay, so in the second region, the periodicity is very much the same as that of the green curve, but there is essentially a difference which is created due to the scattering process, and that difference is delta, and that is called phase shift. Okay, actually the red line should be uh, actually continuous, because these wave functions are well behaved wave functions and they should be continuous at the boundary. So this curve will actually start from where the previous one had stopped. It should be so. Okay. Now let us see. The green curve becomes 0 for this value of R2. So KR2 is pi, is the location where that curve goes through 0. Now, where does my second curve go through 0? It becomes, the second curve is KR plus delta. Okay, so this portion has to become pi. Okay, so my KR1 plus delta becomes pi. That is the location where that curve goes through a 0. Now you subtract these two relations and you obtain an expression for delta. You get delta as k times R2 minus R1. But since R2 is greater than R1, this value of delta is positive. But we had seen from the graph that delta is taking a negative value also. So how do we explain that? For that, if we are considering, instead of an attractive potential, suppose we are considering a repulsive potential. So my potential is something like this. In region 1, it is plus V0. In the earlier case, if you remember, it is minus V0. Okay, this is an attractive potential. Instead of this, you are considering a repulsive potential. So this would be my potential. And if you are solving Schrodinger equation, you will get similar type of solutions, except for the fact that capital K now is root of 2m into E minus V0 by H cross. This comes because of the change in sign of the potential. And here visibly itself you can understand that capital K is less than small k. Okay. So what happens to the wave functions? It is just opposite that of the previous case. To understand, as a reference you are plotting sine small kr and it goes through a 0 at some particular value of R2. Okay. And now you are plotting the wave functions in region 1 and region 2. As we said before, here capital K is less than small k. So capital KR will be less than small kr for the same values of R. Okay. So sine capital KR will become a maximum only at later values of R. Sine small kr will become a maximum earlier, or it will become a maximum faster, and after that only sine capital KR becomes a maximum, and from there it starts receding. But then it will start enter region 2, and in region 2 there is again no potential, and the curve is nothing but a curve is having the same periodicity as sine kr, but it is sine kr plus delta. Okay, there will be a difference between these two curves. This is our reference curve. This is sine kr curve, and this one is sine kr plus delta curve. Okay, there is a difference of delta which is introduced due to scattering. Okay, here also the region 1 and region 2, the wave functions have to be continuous. So it can start only from where the previous one had ended. So it will come like this, and it will follow the same pattern as that of sine kr, except for the fact that there will be a phase shift of delta. Now here if you see, kr2 is pi, is the location of 0 for this sine kr curve, and the location of 0 for this curve, which is sine kr plus delta, that is kr1 plus delta, should become pi. Okay, and if you subtract these two equations and obtain an expression for delta, you will get delta as k times R2 minus R1. But here, my R2 is less than R1. So, delta will be negative. Okay, so the sign of delta tells you whether the potential or my interaction is attractive or repulsive. Okay, so you can just imagine, like if you just recall the scattering graph, phase shift on the y-axis and energy on the x-axis, you see that for energies beyond 300 MeV, delta changes sign. Okay, so now what is it that happens? You just picturize the event like at higher energies, I mean the nucleons have more energy and they get more closer to each other. And when they come more closer to each other, that is where, and that happens at high energies. High energies, there is more likelihood for the neutrons to come more closer to each other. And that is where this delta changes sign. So we should understand that when nucleons are getting more closer to each other, the interaction is becoming repulsive. So for energies up to a particular value, the interaction between nucleons is attractive in nature, and beyond a particular energy, when you are increasing the projectile beam energy, the particles, interacting particles, are coming so close to each other that the interaction is becoming repulsive in nature. Okay, so we should understand that nuclear forces, they operate only in a particular range that is there. If the nucleons are very far apart, nuclear forces will not operate. See, if this is the if suppose this is the range of nuclear forces. Range of nuclear forces means the nucleons have to be, this is the maximum distance that the nucleons can be separated and they can still interact via nuclear forces. If nucleons go beyond this distance, if nucleons are separated beyond R0, they do not interact via nuclear forces. Now, there is some minimum, okay, distance of proximity for the neutrons. If the neutrons, not just neutrons alone, if the nucleons come beyond a closer beyond a particular distance, the nuclear forces become repulsive in nature. They repel each other. Okay. So nuclear forces are not always attractive. They can be repulsive also. It is like this. If the nucleons come closer beyond a particular point, nuclear forces become repulsive in nature. And if the nucleons are separated beyond a particular distance, nuclear forces are not operational. So there is a distance regime in which nuclear forces are attractive. There is a distance regime in which nuclear forces becomes repulsive, and there is a distance beyond which nuclear forces are not operational. So you should actually modify the potential like this. The forces are attractive only in this region, and it has been observed that if nucleons come closer than say zero point 0.5 femtometer, nuclear forces are repulsive. So in this region you have a positive potential. Here you have an attractive potential, and nuclear forces are operational only up to the range of nuclear interaction. Beyond, if nucleons are separated beyond R0, then there is no nuclear force acting between the nucleons. Okay. So such an information we get from high energy scattering processes. Nuclear forces are both attractive and repulsive, and that depends on the distance of separation between the nucleons. Okay. Now we will see something called exchange force model. Exchange force model was actually introduced to explain some observation that we obtained from scattering processes. In scattering processes, it was observed that the scattering cross section was high for low scattering angles. For small scattering angles, as expected, the scattering cross section was high and the scattering cross section fell, and beyond a particular value, we see that scattering cross section is again increasing. That is, for extremely low angles, high scattering cross sections we had expected. But for extremely high angles, again the scattering cross section is high. That we couldn't actually explain, or that was something that was not expected. So, how to explain this observation? That low energies and high energies also the scattering is very likely, or the scattering cross section is very high. How do we explain this observation? So it is in this context that a model called exchange force model was proposed. You can just picturize a scattering event as happening like this. This we have plotted in the center of mass frame of reference. So you can see a neutron coming approaching a target, and when the neutron moves in this direction, you can imagine the proton as approaching from this position, and there is a region of interaction, and neutron goes like this and proton goes like this. Okay, this is in the center of mass frame of reference. Okay, in some cases you are also seeing something like this, a large angle scattering. Large angle scattering means neutrons are scattered at extremely large angles, and something like back scattering and all. Okay, so what is actually happening here? It was proposed that nucleons are actually constantly exchanging some particle with each other, and that is how they are interacting via nuclear forces. So, when we are proposing such a concept of exchange force, we should also keep in mind that when neutron and proton are exchanging a particle, the particle should actually have a charge. It should also have a mass. And you should also keep in mind that neutrons and neutrons, as well as protons and protons, are two interacting with nuclear forces. So the exchange particle between n and p should actually be chargeless. And it should have a mass also. So if a non-zero rest mass particle is being exchanged and a nucleon is remaining a nucleon, it will look like some energy is created out of nowhere. Okay, so it is like, but energy cannot be created like that. That is what we say. Out of nowhere, such an energy creation is not possible. But this energy uncertainty is allowed if it is for extremely short durations. That is by uncertainty principle. Okay, suppose you consider that the energy corresponding to the exchange particle is mc square, m pi c square. You will understand why I mentioned pi later on as we proceed. As per uncertainty principle, delta E delta T is approximately h cross, and delta T is h cross by m pi c square, and the range of the particle cannot exceed c delta T. The maximum speed that you can assume for these particles is the velocity of light. So the range of the particle cannot exceed this particular value. C delta T would be the range. Range is a distance. No. So it is velocity times time. So such an exchange particle can exist for only this time duration. Within this time duration, the exchange can happen. Okay. You can say the lifetime of the particle is something like this. So the range of the particle cannot exceed this particular value, and what is that value? It is C delta T, which is nothing but you multiply this equation by C, it becomes H cross C by M pi C square. Now H cross C is, we know it's approximately 200 MeV femtometer by M pi C square. Now if you roughly take the range as approximately 2 femtometer, and that is what we generally observe for nuclear forces. If range is approximately 2 femtometer, then M pi C square can be obtained approximately as 100 MeV. Okay, so the mass of the particle is approximately 100 MeV by C square. And if you compare it with the mass of the nucleons is approximately 938 MeV by C square. So this mass is not an extremely small mass. Okay, it's a sizable mass when you compare it with this thing. And if you calculate delta T, you obtain it as, say, range is 2 femtometer. 2 femtometer by C would give you your lifetime of the particle. It is 10 raised to minus 23 seconds. Okay, so it's an extremely small time scale. In that time scale, this particle exchange can happen. Okay, and the exchange particles, if you have learned your particle physics course, you will understand that the exchange particles are called pions. And there are three types of pions. There are two charged pions, positively charged and negatively charged, which have a rest mass energy of 139.6 MeV, and a neutral pion also with a slightly less rest mass energy of 135 MeV. Okay, so these are the exchange particles which mediate interactions between neutrons and protons. Now, how they are detected, that part you can go through the textbook on Introductory Nuclear Physics by Kenneth S. Crane. A very detailed experiment has been given in the textbook. The interactions between different nucleons can be represented like this. N plus pi 0 gives a neutron itself. So, neutrons and neutrons interact via exchange of pi 0. Similarly, protons and protons interact via exchange of pi 0. Similarly, a neutron uh, plus pi plus gives proton. Similarly, proton plus pi minus gives neutron. Whatever equations you are writing, please just consider whether the charge is balanced on both sides. If proton is positive charged, neutron is chargeless. So obviously the particle which should be mediating this part would be pi minus. So you just look all these equations whether they are balanced in charge. Okay. This is how nucleons interact via nuclear forces. It is by exchanging particles called pions. So pions are the mediators of nuclear uh, forces. You can say like that. Okay. Thank you.